All right, then let's get started. Good morning, good afternoon, good evening, everyone. My name is Kannan. I'm one of the co-founders at Yugabyte, and it's my pleasure to welcome you all again. And this is a special episode. It's the 50th episode of the Yugabyte Friday Tech Talk series for engineers, by engineers. And my real pleasure to welcome John Meehan, an engineer at Yugabyte, on today's talk. So with that, John Meehan, over to you. Would love for you to just introduce yourself, maybe a little bit about the kind of things you work on at Yugabyte, and then you can get right into the topic from there. And go ahead.
Great, thanks, Kannan. So my name's John. I'm on the DST team. I focus specifically on the storage level, which is what this talk will be about. I've been at Yugabyte for about 2 years. Today's talk is about our new scheduled full compaction feature specifically. But I also want to give plenty of context on compactions in general. So with that, to give you an idea of where we'll be focusing here, this is an image of the layered architecture of Yugabyte. You could think of this as a single node in a universe. And what we're going to focus on specifically is on the storage level all the way down here. The storage level of Yugabyte is broken up into tablets or shards, each with its own RocksDB instance. And so that's what we're going to be focusing on, is the data storage in RocksDB, as well as the compaction queues that manage that storage. When you write data to DocDB, the way we handle that write is first your data gets written to a mutable mem table, which once it reaches a certain size becomes an immutable mem table that eventually, or quickly actually, gets flushed to disk and gets stored as one of these SST files.
Maybe John, just to add one thing which this diagram doesn't show, but in case people are wondering, every write does get journaled in a write-ahead transaction log as well. And this diagram isn't showing that for simplicity. So we write both to a transaction log and to the in-memory mem table. And in the background, some of the things that John is showing here happen, right? Thank you.
Right, yeah, no, that's a great point. This is simplifying things to just the RocksDB level, but there's a ton of stuff happening on top. We'll be focused on how this data is managed on disk. So to start with, I want to give some background on what we call background compactions. What a compaction does is it combines files as they are written to disk into one larger file. So one thing it does is those immutable mem tables that get written to SSTs are very small, and those compact them into larger files so that we're not reading from hundreds or thousands of files every time we're doing a lookup. And similarly, compactions are also used to then compact those slightly larger files into even bigger files, again, to improve our read performance and also to do garbage collecting of any deleted or expired data during the compaction process. There are two algorithms that we use to determine background compactions. I'm going to kind of breeze through this for the sake of time, but the important takeaway is essentially that we are only looking at a subset of the SSTs each time one of these compaction algorithms run. So typically in this situation, it'll find some subset that reach these requirements, and then that is what gets compacted into a new file. So one of these algorithms is called size amplification. And essentially what this is looking for is a situation in which a first or earliest file is about half the size of the next n-1 smaller files put together. So once these files combined have a size of 2x this file, that's an indication that we should compact them together. And similarly, we have a read amplification algorithm that does something very similar, where it is determining when we have at least this min merge with files, such that a subset of those files combined is within a certain ratio of the next largest file. So in this case, these 4 files get compacted with this file to combine to one larger file. However, this is too large and won't be included in the algorithm. It's notable that you can change those ratios, but again, these ratios are chosen to be optimal for write workloads. One thing I
go ahead. Go ahead, John. No, go ahead.
I was just going to say, one thing I should note here is with these files, you can think of these files on the left-hand side, these large files, as the earliest written data. One of the artifacts of our compaction algorithms is the earliest data ends up in these large SSTs, whereas the later data ends up in these smaller SSTs to the right-hand side.
Yeah, so I was going to sort of just add here, like the intuition behind what John is talking about. One way to say it perhaps is that, like he said in this picture, the leftmost files are typically the older files that are getting larger and larger, and you have newer flushed files that are smaller and smaller. So there's this trade-off between trying to compact all the files together and produce one file, or being intelligent, like, hey, I'm only actually going to pick some effective subset that still reduces the number of files dramatically, but without doing too much work. For example, if I have a 100 gig file on the left end and lots of small 1 gig files, it may not be worth compacting all of it to produce a 105 gig file, because you're spending so much energy to merge a 100 gig file with, like, 4 or 5 other 1 gig files. So it may be better to just work on those 1 gig files, compact them together into a 5 gig file, and end up with a 105 gig file as 2 options, because you spent less work but kind of achieved your goal of, like, reducing the number of files, right? So in general, compactions try to pick files which are somewhat near each other. Over time, what will happen is these lots of 5 gig files may end up accumulating, and you may end up with a 40 gig or a 50 gig file. At that point, it makes sense to then merge it back with the 100 gig file, right? So the algorithm essentially tries to pick files which are somewhat of comparable sizes to make it worth its while to merge.
Right, and it in general tries to also grab multiple files and compact them all together, as opposed to just grabbing, say, 2 files, like these 2 files, and compacting just those 2 together, for instance. And as Kannan is pointing out, like that's to minimize the amount of work that's needed to perform the compactions. So these compactions all use a same shared set of resources within a TServer. TServer is in charge of a number of tablets. Each time one of those tablets has a compaction, or in some cases a flush task, these get put into a priority thread pool that essentially determines what compactions are most important. This priority thread pool has a specific number of threads that scale with the number of CPUs. And in general, it prioritizes that flushes are more important than compactions, assuming that they're both using the same thread pool. Small compactions are more important than large ones. This is so that we don't run into a situation where we fall behind on these small compactions and are reading from way too many files, amplifying our reads. And also, background compactions are prioritized over full compactions. This is particularly important during tablet splitting, because a lot of full compactions take place when automatic tablet splitting is turned on. The compaction resources can be controlled by a number of TServer flags. You can control the number of simultaneously running compactions using this background compactions flag. By default, that's set to -1 or auto, so that scales based on the CPUs available. You can also control the compaction and flush rate limit in terms of bytes per second. So this is monitored on the TServer basis by default, and by default you get 1 GB of rate limit per second. You can also control what is considered a large transaction using this size threshold bytes flag. That is a 1 GB threshold by default. And then we also have this SST file soft limit and hard limit. So what these are thresholds that will either throttle the number of writes in terms of the soft limit or completely stop writes to the tablet in terms of hard limit once you reach a certain number of SST files per tablet. So what this does is it determines, hey, we're behind on compactions. We need to slow down our writes so that we can actually catch up on compactions and ensure that we are not reading from way too many files. Okay, so that brings us to the motivation behind this scheduled full compaction work. So an example large tablet after many compactions might look something like this. This pattern, like this specifically is for a 150 GB tablet, but the pattern holds true for even smaller tablets as well. Typically, you'll get the bulk of your data, maybe like 2/3 of your data in this one large SST file. In this case, it's 100 GB large. Then you'll have some smaller SSTs that are maybe in the like 30 GB range, and then some even smaller SSTs that are either freshly flushed or have only been compacted a few times. That will comprise another like maybe 5/6 6th of the amount of data, in this case 20 GB. The important thing here is that this first SST will rarely be involved in a background compaction, and that's based on the algorithms that we just talked about a minute ago. So for many workloads, that's optimal, but there are some workloads in which background compactions may not be enough. One common case is for update and delete heavy workloads. In these workloads, the older data can end up remaining in the older files for extended period of time, and thus can stick around and will lead to read and space amplification. I'll explain that a little more in detail in a moment. This is also a problem for TTL workloads as older data expires over time, but of course the older data lives in those larger files and thus can remain there for quite a while. And this can also be an issue for deletion compliance. Let's say that you have a requirement that deleted data must actually be removed from the system by a certain date. Those deleted tuples could potentially stick around in those SST files for an extended period of time. They won't be queried, of course, but they will still exist unless, of course, you run a compaction that includes those files. So I'm going to walk through a quick example. This example table is just a simple table that has 5 columns, got a primary key, and then 4 random string columns. And let's say this table has 1 million rows inserted into it. So let's say we want to delete one tuple from this table. So tuple 1 is going to be deleted. It's represented as 5 separate key value pairs that are all stored in this SST1. The deletion manifests as a tombstone that's getting inserted into an SST. And so after the flush, this tombstone isn't going to be enough to trigger a background compaction. So you end up with the deleted tuple still in the file, and then this tombstone at the end that indicates that we shouldn't read from that tuple. That's fine in the case of a single deletion, but if you're deleting a lot of tuples, say like a fifth of your data in this case, then you've got tuples deleted in each of your SST files. And you're inserting 200,000 tombstones to indicate that those tuples are deleted. If the tombstone and the tuple that's being deleted are included in the same compaction, then they'll cancel out and both can be removed. But in practice, what will happen is that this file will not be included, and a number of the tombstones will remain, as well as the data that was deleted.
Yeah, and it's worth adding here that this approach to not immediately deleting the old record, but just sort of logically deleting it, stems from kind of two features or two internal aspects, right? One is the fact that Yugabyte uses a log structured storage engine based on LSM, right? So here you always, all the activity, update activity, delete activity, insert activity happens in a log format, and compactions bring things back together. So that is one. But even traditional databases which use more in-place updatable B tree, they too don't immediately delete older records, and Yugabyte also shares that commonality with them, that these databases use multi-version concurrency control, where you may have in-flight transactions which are still reading the older version of the data because their read started at a certain read point, right? So multi-version concurrency control is another reason why deletes are often logical initially, and then in the background, the actual physical deletion needs to happen. Thank you.
Right, yep. So just to touch on the TTL example, this is basically the same as the deletion example, except in this case, you don't have tombstones. These tuples just have a time to live associated with them and are expired, but they still live in this file. The solution is to run a full compaction on this tablet, at which point you'll remove all of that extra data and compact the remaining into one single SST. So that brings us to the scheduled full compactions feature. What full compactions are is what they sound like. They are a compaction that includes all of the SSTs, and they'll all be compacted into a single file. They use the same resources as the background compactions. So any dedicated threads, any CPU cycles that are normally dedicated to compactions, those apply to full compactions, and the same thresholds apply as well. Same with the disk I/O for copying to a new file. They do require disk space for a temporary copy of all the live data in the tablet. I didn't mention this before, but background compactions do as well. It's just more relevant when you're compacting all of the data in the tablet. This tends to be capped if tablet splitting is enabled, as tablets only reach a certain size. But most importantly, full compactions do not require any table level locks, any tuple level locks. This is completely separate from the full vacuum feature in Postgres. It has a similar function, but is very safe to run alongside your workloads, as no lock is required. So the idea behind scheduled full compactions is essentially to allows the user to say, I want full compactions to run every so often. So you do that by setting a TServer flag called scheduled full compaction frequency hours. So this will be the upper bound for how frequently a full compaction should run on each tablet. By default, it's turned off, but some recommended values would be, say, once every month, once every 2 weeks, even once every 7 days is perfectly fine in most cases. We also include another TServer flag that is the jitter factor percentage. What this does is it introduces some jitter into the scheduling such that it reduces the likelihood that tablets are going to be fully compacted simultaneously, and I'll explain that in a moment. By default, we introduce about 33% of jitter into the scheduling, which is recommended for most cases. The main reasons you might want to change this is if you want to know exactly when compactions are going to be scheduled, or if you want, in that case, you would turn this to 0, or if you want to make it so that you don't care how frequently they're scheduled, you might turn this to 100%, in which case it can schedule compactions at any time.
I think the one thing I wanted to add here, John, is just recap some background, meaning for an LSM database, LSM-based storage database like Yugabyte, compactions have been an integral part of the product from almost day one, right? Whereas the ability for our users to specify, and as part of those compactions, some could have been partial compactions, some could have been full compactions. So that was all more automatically decided by the system. But this ability where users can additionally control a certain guaranteed frequency at which these full compactions run is a new feature, and that has been introduced in 2.16 release. Am I correct about that, John?
Yeah, 2.16, 2.17.
And John was one of the engineers that worked on the feature. But yeah, I just wanted to add a little bit of that context. Thank you.
Mm-hmm. Yep. Right. So if you are running in 2.16 or 2.17, what you can do is you can enable the feature by setting the full compaction frequency flag to a value. So in this case, I'm setting the value to 30 days or 720 hours. You don't have to restart. The flag does not require a restart. It's runtime flag. In this case, we're assuming a jitter factor of 33%. So the jitter factor ends up being 10 days or 33% of 30 days. So once the feature gets enabled, we're just going to look at 3 tablets as an example. We will schedule a full compaction for each of those 3 tablets within the first 10 days, i.e. the jitter factor. It'll detect that these have not previously been fully compacted, and so rather than waiting the 30 days, it'll immediately schedule a compaction within that jitter factor. Once the first compaction finishes, it will schedule another compaction sometime between 20 and 30 days. 20 days is calculated as the 30 days upper bound minus the 10-day jitter factor. And that happens for tablet 3 and tablet 2. Each of these have separate pseudo-random intervals, so as to minimize the chance that all 3 of these or all dozens, hundreds of compactions are happening at the same time. And this just continues ad infinitum. Essentially, as soon as one finishes, you can schedule the next and so on. So I know we're running a little tight on time, but I have a quick demo to show what kind of impact this can have.
John, one question. I mean, and it's probably okay if we went like 5 minutes over or something. So, but let's take one of the questions that's come in.
Oh, yeah.
Is the ability to schedule full compactions at the table level, or is it currently applied to all tables in the Yugabyte cluster?
Yeah, so that's a great question. At the moment, it applies to all tables in a cluster. The ability to schedule it or to change the scheduling per table is something that we are working on. But yes, that is currently the feature is turned on at the TServer level and applies to all tables.
Thank you. Yeah.
So to briefly show you the advantages of this feature, I have been running this Cassandra batch time series workload for the last couple of days. And this workload has a default TTL set of 24 hours. The left-hand side has the feature turned off, and then the right-hand side has full compactions running every 3 hours or so. So the first thing you can see, so if you go into one of the tablets, so here I've opened up the RocksDB for the Cassandra table, the time series table, and one of the 24 tablets. I'll note that I have automatic tablet splitting turned off just for simplicity of this demo. So we start with 24 tablets, and that's all there is. If I do an ls on this, you can see the files. So in this case, this 1096 file is the largest file, and it is roughly a little over, let's see.
Maybe you should add the -h option to your ls command.
Yeah. Yeah, good call.
11 gig.
Yeah.
SSD 0.
Yeah, roughly 11 gigabytes. And you can see that the last time that this file was compacted was yesterday at 1913. If I do the same thing on the tablet at the right, you can see that this has a 14 gigabyte file here, but far fewer large files below it. And this was last compacted just a few hours ago. And this is especially noticeable if I pull up the metrics for these two tables. So in the non-scheduled full compaction case, you can see that the size has been climbing and climbing. It's currently at 541 gigabytes, as a large chunk of that data has expired but hasn't been removed. That will eventually be removed, but we can't it's difficult to say exactly when. On the other hand, you have this, the universe with the tablet, the full compaction feature turned on. And you can see once it reached that 24-hour mark, it started actually removing data, and it's settling at a range of about 350 gigabytes per node. So again, that's 350 versus like 540, and this continues to climb. Any questions on any of that?
No, that's good, John. Yeah.
Okay.
This makes sense. I mean, and this is essentially both giving you some level of control to, like you said, for delete compliance, like some users may have compliance requirements, but this is just like, but obviously there's a trade-off. The more aggressively you try to compact, you are using some extra resources, but those resources, as you clarified, are all under that quota. Like we do have a per TServer knobs to say, hey, not more than so many threads and so many megabytes per second of compact flush related activity we will do. So those quotas are still apply, but this is some trade-offs to keep in mind if you too aggressively turn on this feature.
Right. Yeah. No, that's a good point. And in this case, neither of these universes are overloaded. And so you actually don't see any reduction in the throughput on the full compaction side versus the non-full compaction side.
John, another question is, and I think it's related, maybe we just partially answered it, which is like, is there any impact on query performance if a compaction is underway, right? So I think of that as a question independent of whether it is scheduled full compaction or just a background compaction. But then there's also a second part of the question, which says, wondering if it would be best to schedule a compaction during off hours, right? And I think you're going to talk about that a little bit anyway in your next slide, if I remember.
Yep. Yeah, those are great questions. So the answer to whether there is an impact on query performance is essentially dependent on how overloaded your cluster is. If you are not maxing out your CPU cycles and your disk IOPS, then you'll essentially just use those spare resources to run the compaction, and it'll just happen in the background. If you are topping out those two resources, then you can see some performance impact just because it does require some use of those resources. But again, there's no locks involved, so so long as you're not maxing out either of those resources, you won't notice query impact. And the other so the other question is about running. The other question is about running during off-peak hours. So that is one of the future feature improvements. We have had some requests to run during preferred compaction times. So like, for instance, maybe late at night or over the weekend. And that's something we're looking into, finding a way to specify what the preferred compaction times are and scheduling those compactions during those hours. We're also working on a feature to automatically trigger the full compactions when they are needed. So this is particularly helpful for some ranged queries that see a large performance hit when a tablet hasn't been fully compacted for a long period of time. And what we can do is we can recognize that most of our scanning has been dead tuples in some way, shape, or form. And once we recognize that such a huge percentage of the scan is unnecessary work, we can then schedule a full compaction for that tablet automatically, and the user will be none the wiser. It'll just improve performance. And finally, another feature improvement we're looking at is this client-side full compaction status and monitoring. So this will give improved visibility into the full compaction status. So if you run a full compaction on a table or on a full TServer, it will give you an idea of how long that has been running and what kind of progress it's made. I didn't include it on this slide, but we're also looking into specifying the scheduling per table as well, because I know there are many workloads where maybe you want some tables to be compacted regularly and others to be left alone.
Yeah, I think that would be a good one to also add to the slide. But yeah, thanks for covering that, John, that additional request.
Yeah.
There are a few more questions. Okay, so why don't you this we can have the slide on, but let's take some of those other questions. So one of the questions is, can a compaction be stopped and resumed? If so, can we do a lot of work in between?
So there are mechanisms internally that may stop and resume a compaction. We don't have any way to do that manually. Essentially, what happens during a compaction is you are copying all of the relevant data from all of the files into a brand new file. And then once that new file has fully completed, it then deletes all the old files. There's not really usually a great advantage in stopping a full compaction midway, unless, of course, like automatically it might do that in order to facilitate a flush or a smaller compaction.
Yeah, I agree with that, John. Essentially, internally, the system sometimes pauses and resumes a large compaction to prioritize a flush. But this is not something we expose to end users, nor do we think it's probably too low level to do it for the end users. And in general, you have to plan headroom in the system anyway in a log structured engine to have a few cores to be able to do background activity or deal with the fact that another node is down and it has to do extra work to copy. So some headroom, like, a good guideline is to operate your system at sort of 65% CPU utilization and not run it too hot so that it has no bandwidth for this additional background task. And even just like the node failure, when a node is failure, all the remaining nodes have to take up some extra work, right? So that's just good practice. Let's take a few of the other questions. Great talk. I understand it is useful for delete compliance, but probably also for space reclamation, right? And what kind of metric observation would you use to set or alter compaction setting? It's a broad question, but you're absolutely right that it's not just for delete compliance, but it's also to reclaim space for overwritten or deleted data. So that part is true. In terms of the kinds of metrics and observations that we would use to set or alter compaction settings, I think, John, you want to take that? You kind of covered a bunch of flags, right? Usually most users don't really change those flags too much, but do you want to add anything, John?
Yeah, so I mean, most of the flags that I brought up are pretty standard. Like, there's very few times, I would say, when you really want to be tuning some of these flags. As far as observing when you alter compaction settings, so I mentioned this this auto full compactions feature, and what that would be doing is comparing essentially you'd be looking at statistics at the RocksDB level and looking for times where you are doing a large number of RocksDB seeks per seek, right, per data item that you're returning. We're planning on adding an additional metric as well that indicates how many of those seeks are for expired tuples or deleted tuples. I mean, I would say in terms of like TTL or the update or insert workloads, I would say one strong consideration would be if you notice that your read queries are taking a lot longer, have a lot higher latency than you expect. Doing a full compaction on that table can be a pretty safe way to try to fix the problem.
Yeah, and by the way, the system does already export a lot of metrics on how much the flush rate has been, how much the compaction rate has been, and so on. So there is a lot of internal metrics that end users can subscribe to. In fact, some of our dashboards in the platform in the Yugabyte Anywhere product already show that, but all of that is exposed at the TServer layer too, if you're building your own Prometheus or Grafana type integrations, right? Maybe let's just take the last two questions and try to wrap the talk up. If the server is not overloaded, could the DB be more aggressive with compactions? Yes, but currently we aren't doing it automatically. It's still guided by the configured number of priority pool or the compaction threads. We do automatically decide the right setting for it based on, are you running on an 8-core machine or 16-core machine or 32-core machine? But today we don't exceed that threshold just because we find that the server is idle. It's always a catch-22. Like, at the instant we look, maybe the server is idle, and then you start this compaction, but maybe right that next minute server got overloaded. So it's an interesting area, but we haven't gone too deep into that. Let's take the next question. How is compaction affecting the ability to recover from a point in time? And John, if you want to take that, I'm also happy to take that question, whatever you wanted.
Yeah, so that's a really good question. So I didn't mention it in the talk, but there is a separate flag that indicates the history retention that should be maintained in each tablet. So when you run a compaction, it respects that history retention. And so anything that is still within that history retention window will not be deleted or expired. It's still considered live data. So you can configure, you can manage that via that flag. It's like history retention milliseconds or something like that. But that's a great question. And to that point, if you're running some experiments on your own and you're wondering why, when you ran your full compaction, it didn't delete data you expected it to delete, it's likely because of that history retention, because it's set to 15 minutes by default. So unless you waited 15 minutes or reduced that number, it's not going to delete your data.
Absolutely. And for point in time restore kind of feature, that history retention, we increase it based on your snapshot schedule, right? And it is a trade-off. Like you do end up, your ability to reclaim that space is delayed, but all of this still kicks in. Hopefully, like in a typical system, you're not trying to major compact every 4 hours or every 6 days. This is typically something that you probably do maybe once a day or more than once a week or so. So hopefully, they, usually they don't trip on each other. But that's a good insight and insightful question for sure. I know we're way past time. There was 1 or 2 more questions, but we'll probably have to wrap up this talk, John. I really appreciate everybody joining us for the 50th episode. See you again next week. And over to you, John, for the final words.
Thank you so much for coming. Really appreciate it. Just as a plug, there will be 2 blog posts coming shortly, one of them next week and one of them like the week after, that will cover a lot of this information in more detail. So if you're looking for more specific answers to more specific questions, it may be covered in those posts.
All right. See you all. Have a great rest of the week and weekend.
Thank you.